Hello there, and welcome to Simple Sleepy Science. Tonight, we're exploring rainbows, those impossible bridges of light hanging in the sky. You've seen them your whole life, but tonight, you'll discover what they really are. And here's something wild. Every rainbow you've ever seen was yours alone. No one else saw exactly what you saw. Not your friend standing next to you. Not anyone. Each rainbow exists only for your eyes, painted by light and water in a way that can never be repeated. If this brings you calm, if you enjoy these quiet journeys through science, please like and subscribe so you don't miss tomorrow's story. And leave a comment telling me where you're watching from and what time it is there. I love knowing where in the world you are as we explore together. Now, get comfortable. Let your breathing slow. Let's discover the science of something that feels like magic, but is actually something even better. A rainbow isn't a thing you can touch. It's not hanging in the sky like a banner or a bridge. It's an event, a moment of perfect cooperation between sunlight, water droplets, and your eyes. Three things must happen at once. The sun must be behind you. Rain or mist must be in front of you. And your eyes must be at just the right angle. When these three things align, something beautiful occurs. Light from the sun travels in a straight line until it hits something. When it hits a water droplet floating in the air, the light bends. This bending is called refraction. The light enters the drop, slows down because water is denser than air, and changes direction. But here's where it gets interesting. White light from the sun isn't actually white. It's every color mixed together. Red, orange, yellow, green, blue, violet, all traveling as one beam until something separates them. Inside the water drop, different colors bend at slightly different angles. Red light bends the least. It's lazy, taking the gentlest curve. Violet light bends the most, turning sharper. All the other colors bend somewhere in between. This is why a prism splits light into a rainbow. Water drops do the same thing, millions of them at once. But the light doesn't stop there. After bending on the way in, the light hits the back wall of the water drop. Most of it passes through and keeps going, but some bounces off the back surface like a mirror, reflecting back toward the front of the drop. On its way out, the light bends again. 3 bends total, entering, bouncing, and exiting. Each bend separates the colors a bit more. Now, imagine a million water droplets, each one splitting light the same way. Each drop sends every color of light in every direction. Most of that light never reaches your eyes. But at one specific angle, the red light from thousands of drops all reaches your eyes at once. At a slightly different angle, orange light does the same. Then yellow, green, blue, violet. Your brain sees all these colored dots and connects them into a smooth arc. That arc is what we call a rainbow. The drops themselves are falling. They're moving through the air, heading toward the ground. But new drops keep taking their place. The rainbow seems to hover in one spot, but it's constantly being remade by fresh drops at the perfect angle. You're seeing a living thing, rebuilding itself thousands of times per second. Light and water dancing together, and your eyes are the stage where it all happens. Here's where it gets personal. The rainbow you see depends entirely on where you're standing. Not sort of, not approximately, completely. Every single photon of colored light entering your eye came from a specific water drop at a specific angle. Move 10 feet to the left, and those drops have fallen or blown away. New drops are in their place, and they're sending light to your new position. You're seeing a completely different rainbow now. Different drops, different light paths, different colors reaching your eyes. Your friend standing next to you sees their own rainbow. They're not seeing what you see. They can't. The geometry won't allow it. Their eyes are in a different position in space. The angle between the sun, the water drops, and their eyes is different from yours. So the drops sending red light to their eyes are not the same drops sending red light to your eyes. You're both looking at the same general area of sky, both seeing an arc of colors, but the actual light show is unique to each of you. This means every rainbow photograph is a version that only the camera saw. Stand next to someone taking a picture of a rainbow. You're experiencing separate phenomena. The camera captures light from one set of drops at one position. Your eyes capture light from different drops at a different position. If you took your own photo from where you stand, it would show different details, different brightness, even slightly different positions of color bands. The rainbow in the photo is the camera's rainbow, not yours. Think about what this means. Every rainbow you've ever seen was created just for you. No one else in history has seen that exact combination of light and water. Even if 1 million people watched the same storm, each person saw their own private display. The rainbow doesn't exist as an object out there in the world. It exists as a relationship between 3 things: a light source, water drops, and an observer. Change any one of those 3, and you get a different rainbow. This is why you can never walk to the end of a rainbow. It's not a fixed structure with an endpoint. It's an angle. As you move toward where the rainbow seems to touch the ground, the angle changes. New drops farther away are now at the correct angle to send light to your eyes. The rainbow appears to move away from you at exactly the speed you walk toward it. Chase it for miles, and it stays the same distance ahead. It's always the same number of degrees away from the anti-solar point, the spot in the sky directly opposite the sun from your perspective. Walk away from a rainbow and it follows you. Run and it runs. Stand still and it stands still until the sun moves or the rain stops. You're at the center of your own rainbow universe. The arc you see is painted on an invisible sphere around you, always at that magic angle we'll explore soon. Every person gets to be the center of their own rainbow world. We're all standing in the middle of our own private light circles, seeing something no one else can see. The rainbow is democracy of physics. Everyone gets their own. No one's is better or more real. Each one exists perfectly and completely for exactly one person, you. There's a magic number in rainbows, and it's 42. Specifically, 42 degrees. This is the angle between the sunlight coming over your shoulder, your eye, and the center of the rainbow's arc. It never changes. Physics demands it, Every rainbow you've ever seen, every rainbow anyone has ever seen, follows this rule. When light enters a water drop, it bends at a specific angle based on the properties of water. Water has what scientists call a refractive index. For water, that number is about 0.33. This means light slows down and bends when it enters water. The amount of bending is precise and predictable. Red light, with its longer wavelength, bends less than blue light with its shorter wavelength. This happens every time, in every drop, everywhere on Earth. After the light bends on entry, it travels through the drop and hits the back surface. Some light escapes, but some reflects off the back like a mirror. The angle of this reflection is also precise. Then the light travels back to the front of the drop and exits, bending one more time as it speeds back up in air. 3 bends total. Each one follows exact mathematical rules discovered over 1,000 years ago. All these bends add up. When you calculate the path light takes through a spherical water drop, you find that the most intense light exits at specific angles. For red light, that angle is about 42 degrees from the light's original path. For violet light, it's about 40 degrees. Orange, yellow, green, and blue fall between these two. This is why rainbows always appear the same size in the sky. The physics doesn't change. The 42-degree rule means you can predict where a rainbow will appear. If you know where the sun is, you can point to the exact spot in the sky where the rainbow will form, assuming there's rain or mist there. The rainbow's center is always directly opposite the sun from your viewpoint. That's called the anti-solar point. If the sun is behind you and low on the horizon, the anti-solar point is high in front of you, and so is the rainbow's center. If the sun rises higher, the anti-solar point drops, and the rainbow's center drops with it. This is why you never see rainbows at noon. When the sun is directly overhead, the anti-solar point is directly beneath your feet. Underground, the rainbow's 42-degree arc would be mostly below the horizon, hidden by the Earth. You might see the very top edge if you're on a mountain or tall building, but most of the rainbow is pointing down into the ground where you can't see it. Rainbows need the sun to be less than 42 degrees above the horizon. Early morning and late evening are prime rainbow time. The sun is low, the anti-solar point is high, and the full arc can paint itself across the sky. Every culture that studied rainbows discovered this angle. Ancient Persian scientists calculated it. Greek philosophers measured it. Chinese astronomers documented it. The number appears in medieval European texts and in Islamic Golden Age treatises. Everyone found 42 degrees because mathematics doesn't change with culture or language. Water bends light the same way in every country, every century. The rainbow's geometry is universal, one of the few things every human who has ever lived shares exactly. Same angle, same arc, same physics, playing out in countless skies across time. You've only ever seen half a rainbow, maybe a bit more if you were lucky. But rainbows are complete circles. Always. The ground just cuts off the bottom half. You're standing on Earth's surface, and the planet blocks your view of the lower arc. But the rainbow doesn't stop. It continues down below the horizon. A perfect circle of light that would close on itself if nothing was in the way. If you're in an airplane, you can see it. Look down at the right moment, when the plane flies over rain or mist with the sun behind you. And there it is. A complete circular rainbow floating in the sky below. The full wheel of color, unbroken, perfect. It's stunning when you first see it. Something you've known your whole life suddenly reveals its true form. Not an arch, a ring. Stand on a mountain and look down into a valley filled with mist. Same thing. The rainbow circles around the anti-solar point, that spot directly opposite the sun. From high enough, you can see the entire ring hovering in the air below you. Sometimes, you'll even see your shadow projected onto the mist at the center of the circle. That's called a Brockenspector, named after a mountain in Germany where it happens often. Your shadow becomes the center point, and the rainbow wraps around you like a halo. The circle makes sense when you think about the geometry. Remember that 42-degree angle? It extends in every direction around the anti-solar point. Up, down, left, right, and everywhere in between. Imagine a cone of light pointing from the sun through your head to the anti-solar point. The rainbow forms on the surface of that cone at exactly 42 degrees. Slice through a cone and you get a circle. That's your rainbow. The higher the sun climbs in the sky, the lower the anti-solar point drops. When the sun is on the horizon at sunrise or sunset, the anti-solar point is on the opposite horizon. The rainbow's center is right at ground level, and you see a perfect semicircle, half above the horizon and half hidden below. As the sun rises, the rainbow's center drops below the horizon. You see less of the circle, maybe just the top third or quarter. By the time the sun reaches 42 degrees above the horizon, the entire rainbow circle is below ground. Nothing left to see. This is why rainbows are rare at midday in most places. The sun is too high. The rainbow exists, but it's pointing into the earth. Only near the equator during certain seasons, or in polar regions during their summer, can the sun stay low enough all day for rainbows to remain visible. Most of the world has to wait for morning or evening, those golden hours when the sun cooperates with geometry. Waterfalls create permanent rainbow circles if the conditions are right. The mist from the falling water hangs in the air. The sun moves across the sky. If you stand in the right spot at the right time, you can watch a circular rainbow materialize in the spray, hover for a while, then fade as the sun's angle changes. Some waterfalls are famous for this. Yosemite Falls, Victoria Falls, Niagara Falls. Places where enough water crashes down to keep mist constantly floating, waiting for sunlight to paint circles in the air. Sometimes light bounces twice inside a water drop instead of once. When that happens, you get a second rainbow, fainter and higher in the sky above the first. But here's the twist: the colors are reversed. In the primary rainbow, red sits on top and violet on the bottom. In the secondary rainbow, violet is on top and red is on the bottom. Everything flips. This happens because of that second bounce. In a normal rainbow, light enters the drop, bounces once off the back, and exits. Simple path. But some light bounces twice before exiting. It enters the drop, hits the back, bounces to another part of the inner surface. bounces again, then finally exits. That second bounce flips the light's path. Red light, which normally exits at the steeper angle, now exits at the shallower angle. Violet does the opposite. The entire color sequence reverses. The secondary rainbow appears at about 51 degrees from the anti-solar point, compared to the primary rainbow's 42 degrees. That's 9 degrees higher in the sky. It's also much dimmer. Each time light bounces inside a drop, some energy is lost. The light that bounces twice loses more energy than light that bounces once. So the secondary rainbow looks washed out, pale, like a ghost of the primary rainbow. Look carefully at the space between the two rainbows. It's darker than the sky around them. This region is called Alexander's Band, named after Alexander of Aphrodisias, a Greek philosopher who described it around 200 AD. He noticed that the sky between the two rainbows appeared dimmer than the sky outside them. He was right. In that band, light is being bent away from your eyes by the water drops. The drops are sending their light to other angles, other observers, but not to you. You're standing in a shadow zone between the two arcs. Below the primary rainbow, the sky is brighter. Light from drops in that region reaches your eyes even though it's not forming a rainbow. Above the secondary rainbow, same thing. Bright sky. But in Alexander's Band, the geometry creates a gap. No rainbow light reaches you from that specific angular range. The band wraps around the entire circle, just like the rainbows themselves. From an airplane, you'd see it as a dark ring between two bright rings of color. Not every rainbow has a secondary arc. The conditions have to be right. The water drops need to be large enough and uniform enough in size. The sun needs to be bright. The rain needs to be steady. When all these factors align, the secondary rainbow appears, fainter but unmistakable, with its backwards colors announcing that light has taken a longer journey through the drops. Some people go their whole lives seeing dozens of primary rainbows, but never noticing the secondary arc. Once you know to look for it, though, you'll spot it more often. Check above the main rainbow next time. Look for that pale band of reversed colors. And watch for Alexander's Band, that stripe of darker sky between the two. It's subtle, easy to miss, but once you see it, you can't unsee it. The shadow between two circles of light, proof that rainbows aren't just about where light goes, but also about where it doesn't. There are colors in rainbows your eyes can't really see, not because they're invisible, but because they blend so smoothly that they create shades without names. Between red and orange, there's a gradient of 1,000 hues. Between yellow and green, the same. Your brain sees this continuous spectrum and tries to organize it into the color categories you learned as a child. But the rainbow doesn't come in neat bands. It's a smooth flow from one wavelength to the next. No two people see these in-between colors the same way. Your color perception depends on the 3 types of cone cells in your eyes. One type responds best to red light, one to green, one to blue. Your brain interprets the signals from these 3 sensors and constructs what you experience as color. But everyone's cone cells are slightly different. Some people have more sensitive red cones. Others have green cones that respond to a wider range of wavelengths. Your rainbow is colored by your unique biology. Language shapes what you see too. If your language has a word for a color, you're better at distinguishing it from similar shades. English speakers easily separate blue from green because we have clear words for each. But ancient Greek didn't distinguish them. Homer described the sea as wine dark, not blue. Was the Mediterranean a different color 3,000 years ago? No. Homer's language didn't categorize that wavelength the way ours does. His rainbow probably looked different to him, not in physics, but in perception. Japanese traditionally used one word, aoi, for both blue and green. Traffic lights in Japan are called aoi, even though they're clearly green to English speakers. The language is changing now, with separate words becoming more common. But older speakers still see blue and green as variations of one color. Their rainbow has one fewer band than yours. Some cultures name more colors in the rainbow than others. Russians have separate words for light blue and dark blue, treating them as distinct as English speakers treat blue and green. Russian speakers are faster at distinguishing shades of blue. Their rainbow has an extra band where English speakers see one smooth transition. The colors you name are the colors you see. This doesn't mean the wavelengths change. Light is light, vibrating at specific frequencies regardless of who's watching. But the experience of color happens in your brain, not in the sky. The rainbow is filtered through your language, your culture, your individual eye structure. Two people standing side by side see different rainbows, not just because of their position in space, but because of their position in culture and biology. And then there are people with only 2 types of cone cells instead of 3. They see fewer color distinctions. Their rainbow is simpler, with less variation between bands. Meanwhile, a small percentage of women have 4 types of cone cells instead of 3. They're tetrachromats, seeing colors the rest of us can't even imagine. Their rainbow has extra shades, extra subtlety, extra beauty in places where we see smooth transitions. They can point to a spot in the rainbow and say there's a color there, while everyone else sees just a blend. The physics is identical for everyone. Light bending at 42 degrees, wavelengths from 400 to 7 nanometers. But the experience is personal. Your rainbow is colored by your brain, your language, your biology. The light is universal. The perception is yours alone. Rainbows don't need rain. They need water, droplets suspended in air, and those can come from anywhere. The source doesn't matter. Only the geometry counts. Sunlight, water drops, the right angle. That's the complete recipe. Waterfalls create rainbows constantly when the sun hits right. The falling water breaks into millions of tiny drops, creating a permanent mist at the base. Walk around a waterfall on a sunny day, and you can watch rainbows appear and disappear as you change position. The mist stays in place. You move through different angles. Each step reveals a new rainbow made by different drops at different positions. Some waterfalls are designed for this. Viewing platforms positioned where rainbows form most reliably. Letting tourists stand at the exact spot where geometry and mist cooperate. Garden hoses create tiny rainbows on sunny days. Turn on the spray nozzle, stand with your back to the sun, and there it is. A small arc in the spray, just as real as any storm rainbow. The physics doesn't care about scale. A drop is a drop. Whether it falls from a cloud or shoots from a hose, it bends light the same way. Kids discover this accidentally every summer, playing in sprinklers and suddenly noticing colors in the water. Ocean spray paints rainbows in the mist above waves. Stand on a cliff above the sea when waves crash against rocks below. The spray rises, the sun catches it, and rainbows flicker in and out of existence. They last seconds, sometimes less. The spray rises, creates a rainbow, then falls or blows away. New spray takes its place. New rainbows form. It's like watching a breathing thing, rainbows appearing with each wave crash. Even your breath can create micro rainbows on cold mornings. Breathe out on a freezing day and watch the tiny water droplets in your breath catch sunlight. If the angle is right, you might see a flash of color. It's tiny, gone in an instant, but it follows the same rules as every other rainbow. Same 42-degree angle, same wavelength separation, same physics operating at the smallest scale. Firefighter hoses create brilliant rainbows in their spray. In bright sunlight, the powerful stream breaks into countless drops, and rainbows appear in the mist. Photographers love this. Firefighters training on sunny days, surrounded by accidental rainbows. The water is there for practical reasons, but physics doesn't care about intentions. It just bends light wherever it finds the right conditions. Fountain shows in cities time their water jets to maximize rainbow formation. The designers know the sun's path. They know which hours will create the best angles. They position fountains and spray patterns to put water exactly where rainbows will form for people sitting in specific spots. It's engineered beauty, using physics as precisely as any architect uses geometry. Irrigation systems create rainbow fields. Large agricultural sprayers throw water high into the air on sunny days. Farmers see rainbows forming in their own crops, arcs of color hanging over wheat or corn. The water is there to feed plants, but it creates beauty as a side effect. Every droplet becomes a tiny prism, and together they paint light across farmland. Any source of water droplets is a potential rainbow maker. Spray bottles, car washes, swimming pool splashes. Anywhere water breaks into small enough pieces and hangs in air long enough for light to pass through. The rainbow is patient. It waits for the right combination of sun and mist, then appears, perfect and temporary, following rules that never change. On rare nights, when the moon is full and bright, and rain or mist fills the air, you can see a moonbow. It's a rainbow made by moonlight instead of sunlight. Same physics, same angles, same water drops splitting light. But the light source is different, and that changes everything. Moonlight is just reflected sunlight. The moon doesn't generate its own light. It catches light from the sun and bounces it toward Earth. By the time that light reaches us, it's much dimmer than direct sunlight. A full moon is about 400,000 times fainter than the sun. This matters because your eyes work differently. In dim light, you have two types of light sensors in your eyes. Cones see color, but need bright light to work. Rods see in darkness, but can't detect color. In moonlight, your cones barely function. Your rods take over. So when you look at a moonbow, your rods tell you there's an arc of light, but your cones can't identify the colors. The moonbow appears white or pale gray, a ghost rainbow hanging in the darkness. But the colors are there. They're always there. Physics doesn't stop working at night. The water drops still separate wavelengths. Red light still exits at 42 degrees. Violet still exits at 40 degrees. Your eyes just can't see it. Point a camera at a moonbow with a long exposure, and the truth appears. The camera sensor collects light over several seconds, gathering enough photons to reveal the colors. Red, orange, yellow, green, blue, violet, all present, all arranged in the same order they always take. The moonbow has color. You just need technology to see it. Waterfalls are the best places to find moonbows. Victoria Falls in Africa is famous for them. The massive amount of falling water creates constant mist that hangs in the air. On nights when the moon is full and the sky is clear, the moonbow appears in the spray, visible for hours as the moon crosses the sky. Yosemite Falls in California has them too. Cumberland Falls in Kentucky is called the moonbow capital of America because conditions align there several nights a month. The moon needs to be full or nearly full. Anything less doesn't provide enough light. The sky needs to be clear. Clouds block the moon just like they block the sun. And rain or mist needs to be in the right place, directly opposite the moon from where you stand. These conditions don't align often. Most people never see a moonbow, but when you do, it's surreal. A pale arc floating in darkness, almost invisible, like something from a dream. Some moonbows appear faintly colored even to the naked eye. If the moon is exceptionally bright and your eyes are fully adjusted to darkness, you might catch hints of red or blue at the edges. It's subtle, barely there, but some observers report seeing it. The human eye is more sensitive than we give it credit for. In perfect conditions, pushed to its limits, it can detect color in surprisingly dim light. The physics teacher in ancient times could never have predicted this. They saw rainbows in daylight and thought that was the only option. But the rules apply regardless of light source. Sun, moon, even bright streetlights can create rainbow arcs in mist if the geometry aligns. The universe doesn't distinguish between light sources. It just bends whatever light arrives, following the same mathematics every single time. The size of water droplets changes how rainbows look, not just a little, dramatically. A rainbow from large drops looks completely different from a rainbow made by tiny drops. The physics stays the same, but the results shift in surprising ways. Large drops, bigger than a millimeter across, make the brightest rainbows with the sharpest color bands. Each color appears distinct and vibrant. Red is clearly red. Green is clearly green. The boundaries between colors are well defined. This happens because large drops act like clean prisms. Light enters, bounces once, and exits at precise angles. The wavelengths separate cleanly. Your eye receives strong signals of each color from different angular positions. Smaller drops create softer rainbows. As drops shrink below a millimeter, the colors start to blur at the edges. Orange bleeds into red and yellow. Green spreads into yellow and blue. The rainbow loses sharpness, but gains a gentler, hazier quality. You can still see all the colors, but they flow into each other more smoothly. When drops get really small, like the tiny droplets in fog or light mist, something strange happens. The rainbow turns almost white. This is called a fog bow. The colors are technically still there, still separated by wavelength, but they overlap so much that they merge into pale white or grey. The arc is wider and fainter than a normal rainbow. Sometimes you can barely see it, just a suggestion of a bow in the fog. This happens because of wave interference. Light behaves as both particles and waves. With large drops, the particle behavior dominates. Light bounces around inside like a ball. But with tiny drops, wave behavior becomes important. Different wavelengths interfere with each other. They overlap and combine. Blue and violet spread more than red. They start filling in the gaps where other colors should be. Everything washes together into white or very pale color. Cloud droplets are even smaller, usually less than 20 micrometers across. That's a 50th of a millimeter. At this scale, rainbows can't form at all in the traditional sense. The light just scatters in all directions. This is why clouds look white instead of showing rainbow colors. The droplets are too small to organize light into distinct angles. Everything bounces everywhere, and white is what you get when all wavelengths mix. Rain from thunderstorms usually has large drops. Strong updrafts in storm clouds allow drops to grow bigger before falling. These storms produce the most vivid rainbows. The drops are uniform in size, having formed under similar conditions. When millions of similar-sized large drops hang in the air at once, the rainbow appears brilliant and clear. Light drizzle has smaller drops. Drizzle rainbows are softer, more pastel. The colors are gentler, less saturated. If the drizzle turns to heavy mist, the rainbow starts transforming into a fog bow. You can watch this happen in real time if conditions shift during a storm. The rainbow gets wider and paler as the drops shrink, colors bleeding together until only a white arch remains. Professional photographers know this. They seek out storms with large drops for the most dramatic rainbow shots. Large drops mean vivid colors and sharp definition. Small drops mean subtle, dreamy bows that are harder to capture but have their own quiet beauty. The atmosphere decides what kind of rainbow you get by controlling how big the drops grow before they fall. A rainbow is temporary by nature. It exists for minutes, sometimes only seconds. The rain stops, or the sun moves behind a cloud and it vanishes. Not slowly, instantly. One moment it's there, the next it's gone. The drops that made your rainbow are no longer in the right positions. They've fallen to the ground or blown away on the wind. The rainbow doesn't fade. It simply stops happening. New drops take their place constantly. Rain keeps falling. Mist keeps floating. Fresh drops arrive at the exact angles needed to send light to your eyes. So even though individual drops only contribute to the rainbow for a fraction of a second, the rainbow itself appears to hover in place. It's like a waterfall. The water is always moving, always being replaced, but the waterfall stays in one spot. The rainbow works the same way. This means you never see the same rainbow twice. Even if you stand perfectly still for 10 minutes watching a rainbow, you're seeing millions of different rainbows. Each one is made by different water drops. Each drop falls through the critical angle, contributes its colored light, then moves on. The next drop takes its place. Then the next. Then the next. The rainbow rebuilds itself thousands of times per second, each version slightly different from the last. Think about what this means for a photograph. When you capture a rainbow, you're freezing one specific moment, one specific set of drops. The drops in that image existed for maybe 1/100th of a second in the positions shown. By the time you look at the photo, those drops have long since fallen to earth or evaporated. The rainbow in the picture never existed as a stable thing. It was a moment in an endless sequence of moments. The drops themselves are moving fast. Raindrops fall at different speeds depending on size. Small drops fall at about 2 meters per second. Large drops fall at up to 9 meters per second. That's 20 miles per hour for the biggest drops. They're racing toward the ground, and during their fall, they spend only an instant at the perfect angle to contribute to your rainbow. Each drop's contribution lasts milliseconds. Then it's gone, replaced by the drop behind it. Wind changes everything. If wind blows the rain sideways, drops move through the critical angles faster. The rainbow shimmers and shifts. Sometimes it fragments into pieces as gaps appear in the rain. Sometimes it brightens suddenly when a gust brings a thick cluster of drops into position. The rainbow breathes with the wind, alive and responsive to every change in the air. When the rain stops, the rainbow doesn't linger. The last drops fall away. No new drops replace them. The angles empty out. The rainbow vanishes in the time it takes for the final drops to fall below the critical position. A few seconds, maybe less. You can watch it disappear from bottom to top as the lowest drops fall away first, then the ones higher up. The rainbow erases itself, leaving just sky. And when it's gone, nothing remains. The drops are on the ground or evaporated. The light continues on past where the drops were, hitting nothing, bending through nothing. The rainbow was never a thing. It was an event, a temporary alignment of light and water and angle. It happened, then it stopped happening. That's all. There's no end to a rainbow. The myth of a pot of gold sitting where the rainbow touches the ground exists because people thought rainbows were objects with edges and endpoints. They're not. A rainbow is a circle of light, and circles have no endpoints. What looks like the rainbow touching the ground is just the place where the circle dips below the horizon. It doesn't touch anything. It just continues below ground where you can't see it. Chase a rainbow and you'll never catch it. Walk toward where it seems to end, and something strange happens. The rainbow moves away from you, not because it's alive or magical, because it's geometry. Remember, the rainbow exists at a specific angle from your eyes, always 42 degrees from the anti-solar point. When you move, that angle moves with you. The drops that were creating the rainbow for your old position are now at the wrong angle for your new position. Different drops, farther away, are now at the correct angle. the rainbow appears to maintain its distance. It's like trying to walk to the horizon. The horizon is the line where the sky appears to meet the ground. But it's not a place, it's a perspective effect. Move toward it, and it moves with you. You're always the same distance from the horizon, because the horizon is defined by where you're standing. Rainbows work the same way. They're perspective effects, not physical locations. Walk away from a rainbow and it follows you. Run and it runs. It stays locked at that 42-degree angle, no matter what you do. You could drive toward a rainbow at 60 miles per hour and it would pace you perfectly, never getting closer, never falling behind. The geometry is relentless. It doesn't care about your speed or intention. It just maintains the angle. This is why leprechauns supposedly hide gold at the rainbow's end. It's the perfect hiding place because it doesn't exist. You can see it from a distance. It looks like a specific location, but approach it and it vanishes, or rather, it relocates. The myth works as a metaphor. Some goals look concrete from far away, but dissolve when you get close. The rainbow's end is one of these. Visible, but unreachable. Some people have tried anyway. There are stories of people who spent hours driving toward rainbows, convinced they could find where it touched down. They never did. They couldn't. The rainbow stayed ahead of them the entire time, always visible, always at the same apparent distance. Eventually, the storm passed or the sun set, and the rainbow disappeared. Not because they failed to catch it, but because the conditions changed, and the rainbow simply stopped forming. Two people can see the same rainbow from different locations, and both think it ends in different places. You might see the rainbow's base appear to touch down behind a hill 5 miles north. Your friend 10 miles away sees the same rainbow apparently touching ground near a lake to the west. You're both right. You're both wrong. The rainbow doesn't touch down anywhere. It's a circle that extends below the horizon. Where it appears to end depends entirely on where you stand. The pot of gold is the rainbow itself. The real treasure is understanding that some beautiful things aren't meant to be possessed. They're meant to be seen, appreciated, and then let go. The rainbow exists perfectly at a distance. That's where it belongs. When a rainbow appears over water, sometimes you see a second image reflected in the lake or ocean below. But here's where it gets strange. The reflected rainbow isn't in the same place as the reflection of the original rainbow would be. They're two different things entirely. Two separate optical phenomena happening at once. The first rainbow is straightforward. Sunlight comes over your shoulder, hits water drops in the air, bends and bounces, and reaches your eyes as colored light. Standard rainbow physics. But the reflected rainbow takes a different path. Sunlight bounces off the water surface first. Then, this reflected light travels up, hits water drops in the air above the lake, bends and bounces inside them, and comes back down to your eyes. Different light source, different path, different rainbow. Because the light source is different, the geometry changes. The reflected rainbow appears lower in the sky than the original. Sometimes it seems to emerge from the water itself, extending upward. Other times it creates an X pattern with the original rainbow, the two arcs crossing each other. The exact position depends on how far you are from the water and how high the sun is. On rare days, when everything aligns perfectly, you can see 4 rainbows at once. The primary rainbow at 42 degrees, the secondary rainbow at 51 degrees, the reflected primary rainbow created by light bouncing off the water first, and the reflected secondary rainbow also created by reflected light, but with the double bounce inside the drops. 4 separate arcs of colour, each following its own geometric rules, all visible simultaneously. This only happens over calm water. Rough water scatters the reflected sunlight in too many directions. The light needs to bounce off the water like a mirror, maintaining its coherence. Lakes at dawn or dusk when the water is still. Ocean bays protected from wind. These are the places where reflected rainbows appear. The reflected rainbow is usually fainter than the original. Light loses energy when it bounces off water. Not all of it reflects. Some gets absorbed, some refracts into the water. What bounces back is dimmer than direct sunlight. So the reflected rainbow starts with weaker light and ends up creating a paler arc. You have to look carefully to spot it, especially if the original rainbow is bright and draws all your attention. Photographers love this phenomenon. A rainbow reflected in still water makes for dramatic images, but it requires patience. You need the storm to produce rain at the right distance. You need the sun at the right angle. You need calm water. All 3 conditions must align, and they rarely do. Most rainbows over water show no reflection because the surface is too disturbed or the geometry is wrong. Ancient observers noticed reflected rainbows but couldn't explain them. They saw double arcs that didn't behave like normal reflections and invented stories to account for them. Water spirits creating their own rainbows, gods painting multiple arcs for emphasis. The truth is more interesting than the myths. The same light is taking 2 different paths, bouncing off water before entering the drops, creating a second rainbow that follows its own rules while sharing the sky with the first. 2 rainbows, 1 sky, both real, both following physics so precise you can calculate exactly where each will appear if you know the angles involved. At the inner edge of a rainbow, if conditions are just right, you can see faint extra bands of colour. These are called supernumerary rainbows. They look like pastel echoes of the main rainbow, usually pink and green, repeating several times below the primary arc. Most people never notice them because they're so subtle. But once you know to look, you'll see them in almost every bright rainbow made by uniform drops. These extra bands form because light behaves as a wave, not just as particles bouncing through drops. When light takes different paths through a water drop, the waves can meet up again after exiting. If 2 waves line up perfectly, crest matching crest, they strengthen each other. This is called constructive interference. The light gets brighter. If they line up opposite, crest matching trough, they cancel each other out. This is destructive interference. The light disappears. At certain angles just inside the main rainbow, the geometry creates spots where waves from different paths through the drop arrive in phase with each other. These spots glow brighter, creating the supernumerary bands. At other angles, the waves arrive out of phase and cancel. These create the dark spaces between the bright bands. The pattern alternates: bright, dark, bright, dark, getting fainter each time. The drops need to be very uniform in size for this to work. If drops vary too much, the interference patterns from each drop size don't line up. They overlap randomly and blur together. But when all the drops are nearly identical, having formed under similar conditions in the same cloud, their interference patterns synchronize. The supernumerary bands appear sharp and clear. Usually, you see 2 or 3 supernumerary bands, sometimes 4 or 5. The first one is brightest, often pink or light purple with a hint of green. The second is fainter, more greenish. The third is barely visible, a ghost of color that comes and goes. Each band is narrower than the main rainbow's color bands. They squeeze together at the inner edge, creating a delicate fringe. Light drizzle from uniform clouds produces the best supernumerary rainbows. The drops form at the same altitude, grow for the same amount of time, and end up nearly identical in size. Heavy rain from turbulent storms produces drops of many different sizes. The supernumerary bands still form, but they're smeared together and invisible. The uniformity of the drops determines whether you see this phenomenon or not. Thomas Young first explained supernumerary bands in 1804. He used them as evidence that light behaves as a wave. The mathematics of wave interference predicted exactly where the bands should appear and how many you should see based on drop size. When observations matched his predictions, it confirmed that light isn't just particles flying through space. It has wave properties too. Supernumerary rainbows helped prove one of the fundamental truths of physics. Next time you see a bright rainbow, especially during light rain or mist, look carefully at the inner edge. Look just below the violet band. Watch for faint streaks of pink and green. They'll be subtle, easy to miss if you're not paying attention. But they're there more often than you'd think. The wave nature of light creating delicate fringes at the boundary of the rainbow, visible proof that light is stranger and more wonderful than it first appears. Color bands that shouldn't exist, according to simple ray theory, but do exist because reality is richer than simple models suggest. Any world with liquid and an atmosphere can have rainbows, but they'd look different from ours. The physics stays the same, but the materials change everything. Different liquids bend light at different angles. Different atmospheres scatter light in different ways. Earth's rainbows are unique in our solar system because of our specific combination of liquid water, clear skies, and bright sunlight. On Titan, Saturn's largest moon, it rains methane. The atmosphere is thick with nitrogen and methane haze. Lakes of liquid methane cover parts of the surface. If sunlight could pierce through that haze, and if you stood on Titan's surface during a methane rainstorm, you might see rainbows, but they wouldn't form at 42 degrees. Methane has a different refractive index than water. It bends light at different angles. Titan's rainbows would appear at maybe 49 or 50 degrees from the antisolar point. The colors would be different too, because methane absorbs certain wavelengths that water doesn't. Venus has sulfuric acid clouds. The atmosphere is so thick and hot that water can't exist as liquid, but sulfuric acid droplets float in the upper atmosphere. These could theoretically create rainbows, but the clouds are so dense that sunlight barely penetrates. You'd need to be high in the atmosphere, above most of the clouds to see one. The sulfuric acid would create rainbows at its own specific angle, different from both water and methane. Mars has water ice crystals in its thin atmosphere. These don't create rainbows exactly, but they do create halos and arcs. Ice crystals are shaped differently than liquid drops. They're hexagonal, like tiny prisms with flat faces. Light passes through these faces at specific angles, creating circular halos around the sun or moon. Mars has been photographed with ice crystal halos. They're cousins of rainbows, similar physics, but different geometry. Jupiter's atmosphere has ammonia and water droplets, but the environment is so turbulent and strange that any rainbow would be distorted beyond recognition. The extreme winds would stretch and tear the arcs. The thick atmosphere would scatter light in chaotic ways. If rainbows form in Jupiter's clouds, they're nothing like what we see on Earth. On a planet orbiting a red dwarf star, rainbows would shift toward infrared. Red dwarfs emit most of their light in the red and infrared spectrum. Water drops would still separate wavelengths, but most of the rainbow would be invisible to human eyes. You'd see a faint red arc, maybe some orange, but most of the spectrum would extend into wavelengths we can't detect. A planet around a blue giant star would have rainbows that extend deep into ultraviolet. The visible part would be rich in blue and violet, but most of the rainbow would be beyond our vision in the opposite direction. Alien eyes adapted to different star types would see rainbows we can't imagine. Earth sits in a perfect zone. Our sun emits strong, visible light. Our atmosphere is clear enough to let it through. We have liquid water that falls as rain. We have observers who can appreciate it. Every rainbow you see is Earth's signature written in light. No other planet in our solar system can claim this. Our rainbows are as unique to Earth as our blue oceans and green forests. They're markers of a world where conditions align in exactly the right way to paint light across the sky. Scientists have known for centuries that third and fourth rainbows are theoretically possible. The mathematics predicted them. Light could bounce 3 times inside a water drop, or 4 times, creating additional rainbows. But nobody could see them. They were ghosts in the equations, proven by math, but invisible to human eyes. The problem is location. Primary and secondary rainbows appear opposite the sun. You look away from the sun to see them. But third and fourth rainbows appear on the same side of the sky as the sun. To see them, you'd have to look toward the sun. The sun's glare washes everything out. Even if the rainbows are there, the brightness blinds you to them. They're also incredibly faint. Each time light bounces inside a drop, energy is lost. Some light escapes through the drop's surface. Some gets absorbed. By the third bounce, very little light remains. By the fourth bounce, almost nothing. The rainbows form, but they're so dim that they're nearly impossible to detect against the bright sky near the sun. For centuries, these rainbows existed only in theory. Scientists could calculate exactly where they should appear. The third rainbow should form at about 40 degrees on the sun side. The fourth at about 45 degrees on the sun side. The math was solid. The physics was sound, but no one could actually observe them. Then, in 2011, a photographer in Germany named Michael Grossman captured them. He used special techniques to block the sun's direct light. Polarizing filters, careful positioning behind trees and buildings, long exposure times. He photographed storm clouds at the exact angles where theory predicted the third and fourth rainbows should be. And there they were, faint arcs of color, barely visible, but unmistakable once you knew what to look for. His photographs confirmed predictions made hundreds of years earlier by mathematicians who could only imagine what these rainbows looked like. René Descartes, in the 1600s, calculated where they should appear. He worked out the paths light would take with 3 and 4 internal reflections. He knew the angles, but he never saw them. Nobody did until 2011. The third rainbow appears as a faint arc below the sun. Its colors are arranged the same as the primary rainbow, red on top. The fourth rainbow sits above it, colors reversed like the secondary rainbow. Together, they form a pair of faint echoes of the main rainbow system, visible only in perfect conditions, with special equipment to block glare. Even now, very few people have seen third and fourth rainbows. You need the right storm at the right time. You need something to block the sun's direct light. You need to know exactly where to look. And even then, they're so faint that cameras capture them better than eyes. The human eye can barely detect them. But they're real. They exist. Light is bouncing 3 and 4 times inside water drops, creating these ultra-rare arcs. Every rainbow you see has invisible cousins. The third and fourth orders are always there, always forming, just hidden by brightness and glare. The mathematics guarantees it. Light follows the rules. It bounces multiple times in every drop. Most of those bounces produce light too dim or too poorly positioned for us to see. But they happen. Physics doesn't care if we can observe something. It operates whether we're watching or not. Light in rainbows is polarized. This means the light waves vibrate in specific directions, instead of all directions at once. Normal sunlight vibrates in every possible direction. But when light bounces inside a water drop, something changes. The reflection organizes the light waves, making them vibrate mostly in one plane. This creates polarization. You can test this yourself. Look at a rainbow through polarized sunglasses. Rotate the glasses slowly. The rainbow will brighten and dim as you turn. When the polarizing filter aligns with the rainbow's polarization, the light passes through easily. The rainbow looks bright. When the filter sits perpendicular to the polarization, it blocks the light. The rainbow darkens or disappears entirely. Turn the glasses 90 degrees and the rainbow reappears. Some animals see polarized light naturally. Bees navigate using it. They can detect the polarization pattern of the sky even when clouds hide the sun. To a bee, the sky is covered in invisible directional arrows pointing toward the sun. Many birds see polarization too. It helps them navigate during migration. Fish use it to detect predators and prey. The underwater light environment is full of polarization patterns. To these animals, rainbows might look completely different. They'd see not just the colors, but the polarization structure. The rainbow would have patterns and contrasts invisible to human eyes. Certain parts might appear brighter or darker based on polarization rather than color. It would be like seeing an extra dimension of information in the same arc of light. Cuttlefish and squid use polarized light to communicate. Their skin can create polarized patterns that other cuttlefish see, but many predators don't. It's a secret visual language. If a cuttlefish could see a rainbow, it would see both the color spectrum and the polarization, creating a double rainbow of sorts. One made of wavelength, one made of light orientation. Mantis shrimp have the most complex eyes known. They can see polarization in ways we barely understand. They detect circular polarization, which twists like a corkscrew as it travels. To a mantis shrimp, a rainbow would be unimaginably rich with information. Colors we can see, colors we can't see in ultraviolet, linear polarization, circular polarization, all at once. Their rainbow would be so information-dense compared to ours that it's almost a different phenomenon entirely. Humans are mostly blind to polarization. Our eyes can detect it very faintly under specific conditions. Some people report seeing Heidinger's brush, a faint yellowish pattern that appears when looking at polarized light. But it's subtle, easy to miss, and most people never notice it. We evolved without needing polarization vision, so we lost it or never developed it fully. Cameras can capture polarization with special filters. Photographers use polarizing filters to reduce glare from water or glass. Those same filters can enhance or suppress rainbows. Want a more vivid rainbow in your photo? Rotate the polarizing filter until the rainbow's polarization aligns with it. Want to remove a rainbow that's cluttering your composition? Rotate the filter 90 degrees and the rainbow vanishes. The light is always polarized. Every rainbow you've ever seen carried this hidden property. It's there, in the physics, encoded in how the light bounced inside the drops. But unless you have polarized sunglasses or specialized eyes, you'll never see it. The rainbow has layers of complexity beyond color, dimensions of light we can measure but not perceive. The full rainbow exists beyond human vision. You can make rainbows indoors with nothing but water and light. The same physics that creates rainbows in the sky works just as well in your home. Fill a glass with water and set it on a windowsill in direct sunlight. Position a white wall or piece of paper nearby. The glass acts as a prism. Light enters the water, bends, reflects off the far side of the glass, and exits at an angle. On the wall, you'll see rainbow patches. Not a full arc, but the same colors in the same order. Red, orange, yellow, green, blue, violet. A CD or DVD creates rainbows without any water at all. The disk surface is covered in microscopic grooves, tracks of data stamped into the plastic. These grooves are spaced so closely together that they act like a diffraction grating. Light hitting the surface splits into colors. Tilt the disk, and the rainbow shifts and changes. The colors swirl across the surface, bright and metallic. This isn't exactly the same as a water drop rainbow, but it's close. Both phenomena separate white light into its component wavelengths. Soap bubbles show rainbow colors, but for a different reason. The bubble is a thin film of water with soap molecules on both sides. Light reflects off both the outer surface and the inner surface of the film. These two reflections interfere with each other. At some points, they strengthen certain colors. At other points, they cancel colors out. The result is swirling rainbow patterns that shift as the bubble's thickness changes. Thicker parts show different colors than thinner parts. The bubble becomes a moving map of its own structure, written in light. Prisms are the classic indoor rainbow maker. A triangular piece of glass held in sunlight splits the light into a spectrum. Isaac Newton used prisms to prove that white light contains all colors. He let sunlight pass through a prism, saw the rainbow, then passed that rainbow through a second prism. The colors recombined into white light again. This showed that the prism wasn't adding color to the light. It was just separating colors that were already there. Even a diamond's sparkle comes from the same physics. Diamonds have a very high refractive index. Light bends sharply when entering a diamond. The gem's cut faces are positioned to bounce light around inside, bending it multiple times before it exits. All this bending separates wavelengths. White light enters. Rainbow flashes exit from different faces. That's why diamonds sparkle with color. They're splitting light like tiny prisms. Oil slicks on wet pavement create rainbow patterns. The thin film of oil on water works like a soap bubble. Light reflects off both the top and bottom of the oil layer. The reflections interfere. Different thicknesses of oil create different color patterns. The rainbow swirls and flows as the oil spreads and thins. We've brought the physics of rainbows inside, tamed them, made them decorations and tools and jewelry. Every glass of water in sunlight is a potential rainbow maker. Every reflective surface can split light. Every transparent material with the right shape can separate wavelengths. The rainbow isn't confined to storms and mist. It's everywhere light meets matter and bends. We live surrounded by rainbow physics, playing out on small scales in ordinary objects. The same rules that paint arcs across the sky also paint colors on soap films and CDs and glasses of water sitting peacefully in afternoon sunlight. Humans have always wondered about rainbows. Before anyone understood refraction or wavelengths, people saw these impossible arcs in the sky and needed explanations. Every culture created stories. The physics was the same everywhere, but the meanings changed with each civilization. Ancient Norse mythology said rainbows were Bifrost, the bridge between Midgard and Asgard. Earth and heaven connected by light. The gods walked across rainbows to visit the human world. When the rainbow appeared, it meant the boundary between worlds had thinned. The bridge was open. Thor crossed it regularly, his hammer on his shoulder, traveling between realms on an arc of color. In Christianity, the rainbow became a promise. After the flood, God placed a rainbow in the sky as a sign to Noah. No more destroying floods. The rainbow was a covenant, a contract written in light. Every rainbow reminded believers of that promise. It became a symbol of hope after disaster, beauty following destruction. Irish folklore filled rainbows with leprechauns and gold. The little men hid their treasure at the rainbow's end, knowing full well that no one could reach it. The myth captured something true about rainbows, even without understanding the physics. They're unreachable by nature. The treasure is the rainbow itself, not what waits at its base. Chinese tradition saw rainbows as bridges between heaven and earth, similar to Norse mythology, but with different implications. Heaven wasn't a place for gods alone, but a realm of ancestors and cosmic order. The rainbow connected the living and the dead, the mortal and the eternal. It was a path souls could travel. Aboriginal Australians believed rainbows were rainbow serpents, powerful creation spirits. These beings shaped the land, carved rivers, and created water sources. The rainbow serpent lived in waterholes and emerged during rains. See a rainbow, and you were seeing the serpent's body arching across the sky. It was both respected and feared, a force of nature that brought life through water, but could also bring destruction through floods. The Navajo saw rainbows as paths of sacred spirits. They appeared in sand paintings and ceremonies. Walking under a rainbow was forbidden in some traditions. It was holy path, not meant for human feet. The rainbow connected sacred spaces and times, making the ordinary world temporarily divine. Nearly every culture has rainbow stories. Vikings, Greeks, Africans, Native Americans, Polynesians, all created meanings for these arcs of light. The rainbow became universal in human experience, not just as a physical phenomenon, but as a symbol. We've used it to represent hope, promise, diversity, pride, dreams, impossible wishes. It appears in flags and logos and art. It's shorthand for beauty and optimism. All because light bends when it passes through water. All because of a 42-degree angle and the separation of wavelengths. Physics created something so striking that every human culture needed to explain it. We couldn't just let it be light and drops. We had to give it meaning, weave it into our stories, make it represent our hopes and fears. The rainbow transcends science. It's accurate to say a rainbow is refracted light at specific angles. But it's also true that a rainbow is hope appearing after a storm. Both explanations are valid. One describes the mechanism, the other describes the meaning. Humans need both. We need to understand how things work and what they mean to us. Some rainbow phenomena are so rare that most people live entire lives without seeing them. These aren't myths or legends. They're real optical effects that require such specific conditions that they border on impossible. But when they happen, they're proof that light and water can create stranger things than we usually witness. Twinned rainbows are one of the rarest. These appear when light passes through a mix of two different drop sizes at the same time. The two sizes create two slightly different rainbow arcs that don't quite line up. They split apart at the top or bottom, creating a shape like a forked path. The two arcs share some sections but diverge in others. It looks wrong, like someone painted two rainbows and misaligned them. But it's real, caused by rain falling through different atmospheric layers with different drop distributions. Reflection rainbows happen when sunlight bounces off a body of water before hitting raindrops. We covered standard reflected rainbows earlier, but sometimes the geometry creates even stranger versions. The rainbow can appear inverted or in impossible positions, arcing where no rainbow should be. These require large, calm water surfaces and specific sun angles. Lakes at dawn or dusk produce them occasionally. Circumzenithal arcs are upside-down rainbows that appear directly overhead. They're not true rainbows because they form in ice crystals, not water drops. The crystals need to be flat, hexagonal plates floating horizontally in the upper atmosphere. Sunlight enters through one face, bounces inside, and exits through another face at specific angles. The result is a bright arc of color curving upward instead of downward. It only appears when the sun is low and only lasts minutes. Red rainbows occur at sunrise or sunset, when the sun's light is already filtered through so much atmosphere that only red wavelengths remain. All the shorter wavelengths, blue and green and yellow, have scattered away. The rainbow forms, but it's monochrome, a single band of red arcing across the sky. No other colors exist in the light to separate. It's eerie and beautiful, a rainbow reduced to its simplest form. Full circle rainbows from airplanes sometimes appear with the airplane's shadow at the center. This is called a glory. Light hits cloud droplets below the plane, bounces in complex ways involving both refraction and diffraction, and returns to the plane in a circular pattern. The rainbow circles the airplane's shadow like a halo. From inside the plane, passengers see a dark spot surrounded by colored rings, both centered on the point directly opposite the sun. Fogbows occasionally show faint color at their very edges, while remaining white in the center. The edges catch just enough contrast to reveal red on one side and blue on the other. The middle stays ghostly white because the tiny drops scatter wavelengths too thoroughly to separate them. Each of these phenomena appears maybe once in a lifetime for most observers. Some people chase them deliberately, traveling to places where conditions align. Weather forecasters study atmospheric data looking for the perfect combinations. Photographers wait for hours in the right spots, hoping conditions will materialize. But most rare rainbows appear to random observers who just happen to be in the right place at the right moment. Someone looks up during an ordinary rainstorm and sees something impossible: two rainbows splitting apart. A red arc at sunset, a glory from a plane window. These moments can't be predicted perfectly. They're gifts from physics, surprises from light and water cooperating in unexpected ways. The next time you see a rainbow, remember this: you're standing at the center of a perfect circle of light. The rainbow exists because you're there, in that exact spot, at that exact moment. Move 10 feet and you see a different rainbow made by different drops. The rainbow you're seeing is yours alone. No one else can see it. Not your friend standing next to you. Not anyone. It's made of millions of water droplets, each one smaller than your fingernail, each one refracting light at exactly 42 degrees. Every drop contributes for only a fraction of a second before falling away, replaced by the drop behind it. The rainbow rebuilds itself thousands of times each second, always at the same angle, always in the same place relative to the sun and your eyes. Walk toward it, and it walks away. The geometry won't let you catch it. The rainbow is an angle, not a location. It exists in the relationship between three things: sunlight, water, and you. Change anyone and everything changes. The rainbow moves because the angle must be maintained. Physics is strict about this. The rules don't bend. And when the rainbow fades, it doesn't go anywhere. It simply stops happening. The rain ends, or the sun hides, or the angle shifts. the drops that were creating your rainbow fall to the ground. No new drops take their place. The light continues on, but there's nothing left to bend it. The rainbow ceases to exist, not because it went somewhere, but because the conditions that created it changed. Until next time, until the sun and water and your eyes align again in that perfect geometry. And when they do, you'll know what you're really seeing. Not magic, though it feels like magic. Something better. Physics. Performing a trick so perfect, it fooled every culture in human history into calling it divine. Light splitting into colors because water bends different wavelengths at different angles. Simple, predictable, repeatable, and somehow, because we understand it, more beautiful than any myth. Every rainbow is temporary. Every rainbow is unique. Every rainbow is yours and no one else's. These three facts make rainbows precious, in a way that permanent things can never be. You can't own a rainbow. You can't keep it. You can only witness it for the brief moments it exists, and then let it go. The next time you see one, stand still for a moment. Watch it. Remember that you're seeing light that left the sun 8 minutes ago, traveled 93 million miles through space, entered Earth's atmosphere, hit millions of falling water drops, bent 3 times inside each drop, and arrived at your eyes at exactly the right angle to create color. All of this happened so you could see an arc in the sky. And then it will fade, and you'll go on with your day, and eventually you'll see another rainbow, and another, each one different, each one yours, each one following the same physics that's been painting light across skies since Earth first had rain and sun at the same time. If you enjoyed this journey through the science of rainbows, please subscribe so tomorrow night we can explore together again. Leave a comment about where you're watching from. I love knowing where in the world you are as you rest. And if this brought you calm, hit that like button. More peaceful science waits for you tomorrow night. Until then, let your mind settle. Let these thoughts about light and water carry you gently towards sleep. Sweet dreams.